So welcome everyone to today's talk in the Multi-Agent Systems talk series. This is organized by the Multi-Agent Systems Special Interest Group, which is part of the AI program at the Alan Turing Institute. And my name is Stefano Albrecht. I'm the host of these meetings together with Michael Woodridge. And I'll just start off by telling you a few things about the Special Interest Group before I hand over to today's speakers. So first of all, I hope you can see my slides here. They should be in full screen.
Yep.
So we started last year in February when we organized a seminar, Multi-Agent Systems Symposium. And this was a really good event. It was successful. We basically tried to invite all the UK-based labs in universities, industry, and defense who have an interest or a focus in multi-agent systems research to come together and map out the landscape of the research that exists in this area in the UK and the various labs, and do some networking. So this was a really good initiating event. And from after that event, we created this special interest group, which exists at the Turing to continue to organize these meetings. And one thing we're doing now is these online multi-agent systems talks, which take place once a month. We already had 2 talks, and today we have the 3rd talk. Just to tell you more about what the interest group does. So at the bottom of this slide, you can see the URL for the web page. There are basically 3 main activities. We did organize one symposium. We were trying to organize one again once the conditions have relaxed again a little bit. And in the meantime, we're organizing these online talk series. We created this online labs map where we try to kind of map out the landscape of UK-based labs that exist that work in multi-agent systems research. So you can look this up on the special interest group page, which you see at the bottom here. And if you have a lab and you're not yet listed on this, or you're not yet pinned down on this map, then feel free to contact myself and Mike Woodridge, and we're happy to add you to this along with some basic details. And of course, we have a mailing list, which by now we have about 300 people signed up to, so it's really grown a bit. And this can be used by people to advertise opportunities or initiatives that relate to multi-agent systems research, and in particular with a focus on UK. So these are just a few things I wanted to say. And with that, I'm really pleased to introduce today's speakers. We have Nick Hawes and Bruno Lacerda from the Golds Lab at the Oxford Robotics Institute at the University of Oxford. And with that, I'll just hand over straight to Nick. Thank you very much for your talk today, Nick.
Cool, and thank you very much for the introduction. Right, let me share my screen. Is that visible? Are we good?
Yes.
Excellent. Cool. Well, thank you very much again for the introduction. My name is Nick Hawes. I'll be delivering the first sort of 10 minutes of this, and I'll hand over to my colleague Bruno, who'll deliver the rest. So I'm going to start by saying a little bit about the group that Bruno and I run at Oxford and our kind of general philosophy for how we think about the problem of kind of planning behavior for autonomous systems, autonomous robots particularly. And then Bruno's going to give us the kind of multi-agent perspective on that, where we address some of the challenges that are particularly present in multi-robot systems. So a little bit about the group to start with. So we work on sequential decision making for autonomous systems. So the general problem is, how do you sequence a set of actions in order to achieve a goal? So the goals group comes from the fact that we're really interested in goal-driven or task-driven behavior. And in general, we work on a kind of a set of topics that are loosely called mission planning. So we think about what a robot will do for the next minute, 10 minutes, hour, day, week, month. We're particularly actually interested in long-term autonomy, and that's where our history lies in terms of planning missions for robots that can last days or months. So we're really interested in those kind of topics. And because we work on robots, we're also interested in the problem of doing that under uncertainty. So uncertainty is just inherent in robotics, whether that's uncertainty due to kind of the probabilistic nature of state estimation of a robot working where it is in the environment, or whether it's due to partially observable worlds or partially specified models. There's all different sources of uncertainty, and it makes this problem of action sequencing, action selection very challenging. So that's one of the things we're particularly interested in. And within the kind of space of work we do, there are kind of two key topics that really kind of come about, and we're interested in the interplay of these. So the first one is this problem I've talked about just on the previous slide. So mission planning, task planning under uncertainty. So the effects of the actions that the robot performs maybe have uncertain outcomes, or the state the robot is in could be uncertain. But what we want to do is deliver robot kind of mission plans or policies that have some kind of formal guarantees. So before the robot acts, or while the robot's acting, we can say something either quantitative or qualitative about the performance we expect from that robot. So this is typically not just expected reward or expected value. We're interested in much richer behavior specifications that might use linear temporal logic, that might use multi-objective reasoning, that might use conditional value at risk. So rich behavior specifications that allow you to say something formally about the properties of those robot behaviors. In general, you can think about that as a sort of quality of service guarantee, right? When you deploy your multi-robot system or your robot system, you want to know in advance some properties of that robot so that you know the kind of quality of behavior you're going to get back. A lot of what we do is model-based or model-driven. So to do planning, particularly over long time horizons, you need to have a model which you can search or run some optimization on to find this sequence of actions. So we are very much kind of model-driven or model-based lab. But because we're doing robotics and we're doing robotics in the real world, we typically have to think about how we get those models, where those models come from. So we work on planning, but we also think a lot about how the robots can gather their own models or instantiate those models online with a mixture of sort of statistical estimation and machine learning. So we're really, these robots have models that allow them to plan better. If those models are terrible, then the plans will be terrible and the guarantees will be terrible. We're interested in how online the robot can observe its environment, get experience, and use that experience and the data to build better models, or, for example, better quantify the uncertainty that's present in its environment. So for us, these topics go really well together. You want to be able to plan to act longer. As you act longer, you get more information for your model. So your model gets better, your plans get better, and there's kind of a virtuous cycle there. And so we think a lot about these kind of topics and how they interact. To give you a very brief overview of how we think about the world and the models we use, we'll focus on a single agent example. And as I said, Bruno will then take over into the multi-agent example. So pretty much everything you're going to see today features mobile robots. Mobile robots operate in a map typically, which for our case is largely two-dimensional, looks a bit like this. So this is an example robot map. You can then sort of say, well, we can't plan in this continuous space, so we're going to discretize it. And typically our discretization uses some kind of graph. So we locate places in the world and we join them by edges. So we end up with a graph. And as computer scientists, you go, well, if it's just a graph search problem, we know how to do that. But because it's a robotics problem, there are lots of interesting angles to it. First of all, we have to situate the kind of actions the robot can perform. And they often occur on the edges of these graphs because they're different types of mobility. And we also think about the tasks the robot can perform, and we link them often to the nodes in these maps. So they may be looking for objects or learning what people are doing. But it's still not just kind of pure graph search, because these actions and these, whether they're tasks you do or actions you perform, are prone to failure. So the actions might be prone to failure due to the robot having a partially known model of the environment. So that means there are obstacles there it can't navigate, but it didn't know until execution time. Or it might be uncertain due to the duration it takes the robot to perform an action. And that's something you'll hear quite a lot about today, because duration is a key problem in multi-robot coordination. You need to know how long actions take. So the picture you see at the bottom is actually a KDE plotted of the durations a robot took waiting at a doorway for that door to open. So the robot has to wait for a human to open the door, but there is uncertainty in the length of time it has to wait for that door to open. So these kind of different types of uncertainty are just everywhere in robot problems. So in order to do mission planning on with this kind of data, we need to have a model that allows us to capture the uncertainty and the quantitative and qualitative aspects of the robot's experience. So to do that, we use Markov decision process models. And I'm going to give you a kind of a basic overview of what an MDP is, so Markov decision process, then Bruno will specialize those. We're going to try and stay pretty not technical. That was the brief, not to be too technical, but we will reference the models a bit because that really is kind of key to what we do. So an MDP model has states and actions, which are kind of the qualitative part, the discrete part of it. And then they have transition probabilities and action costs. And the way we think about the world is that the states and actions available in this model are often defined a priori by the structure in the robot's environment, by its map, by its task. And the transition probabilities and action costs are learned from experience. They come from this data we get from the robots. So if we map that to the navigation task, so the map you saw previously, the locations will turn into states. So the nodes in the graph help define the states the robot can move through. And then we might have an action, which is to navigate between two locations. So we may have the action of moving from node 1 to node 2. And because of the dynamics of the environment, maybe that's only successful 85% of the time. So we'd say the transition probability of transitioning from N1 to N2 with this action is say 0.85. And then maybe 10% of the time you end up at some other node. And then 5% of the other time you fail because you get stuck and the human has to recover you or something. So this is kind of an individual action, and the probabilities here will come from the experiences of the robot in the environment. But we also think about other features that really start to specify, kind of more closely related to the task the robot's doing. So we may think about durations, we might think of costs in terms of time, or we may think of things like absorbed dose of radiation. So we've been working in a national project called RAIN, looking at robotics in the nuclear context. And here we'll model an MDP where the absorbed dose of radiation is a cost that we may want to optimize when the robot's performing a task. So there's different ways of injecting different cost models into these kind of tasks. So that's the basic model we use. So that was a single action. You can then imagine this is now replicated across the entire map, and we're putting in different types of structures that the robot will work with. And overall, we get an MDP that's kind of tailored to that robot's environment. So that's the sort of single agent part of it. At this point, I'm going to hand over to Bruno, who's going to show how we've specialized this in various ways for the multi-robot problem. Okay, Bruno, over to you.
Hello, everyone. I'll start sharing my screen.
Cool. While you're doing that, I'll just answer the question. So the question in the chat said, how do you find the nodes in the graph in the environment? So those are manually specified typically. You can do them automatically while you do SLAM from a pose graph, for example. You can use them during exploration. In the work we're showing there, the location of the nodes are often tied to the tasks that a human wants the robot to do and kind of branching points in navigation. So those are manually specified because that is part of the user knowledge of that task. I hope that answers the question. Bruno, over to you.
Cool. Okay, so hi everyone, my name is Bruno. I am a senior researcher in the Goals group. And yeah, as Nick said, I'm going to talk to you a bit about the work that we have been doing in the Goals group regarding planning under uncertainty for multi-robot systems. Okay, so just to give you a quick idea of what's going to happen here, we are going to start from or get from the single robot case to the multi-robot case. So if you look at the model that Nick had before, it had just one robot running around. Now we can imagine a similar model with still nodes and edges of the environment, but we can imagine that we have two robots that want to navigate across this environment. Then there's a lot of considerations that we need to take into account when we go from one robot to more than one. First of all, as we also already had for one robot, there is uncertainty in action duration. We have robots in the world. There's inherent uncertainty that can come from the sensor of the robots or its actuators, that can come from under specification of certain parts of the world, many different sources. When you start thinking about execution with more than one robot, then this uncertainty starts becoming even more important, in particular, the uncertainty over the duration of actions. Why? Because if you want smooth execution of these robots, you want to. So if you consider this here, Betty the blue robot and Barney the yellow one, if Betty wants to navigate from this location to this location here, for example, Betty shouldn't be trying to synchronize with Barney at every time step. So Betty navigates to this node V3, and she should continue immediately to node V2. Nothing on its task requires Betty to synchronize with Barney. So we want this execution to be completely asynchronous, and robots should only communicate when they really need to. And because there is uncertainty over the action duration, we really need to model it properly so that we can take into account where other robots might be in the environment when we are doing our execution. There's also this consideration on rich behavior specification. Nick already mentioned some of the type of guarantees that we think about for a single robot. And what I'm gonna call those here in the context of multi-robot systems local guarantees. So these are guarantees that are assigned to one single robot, and we can think about the probability of achieving some task that might be specified in temporal logics. For example, we can talk about the expected duration to achieve that task. We can talk about the probability of the robot exceeding a threshold on the amount of battery it can consume. Okay, so these are the kind of properties that we can think about at the local level. Now that we have a multi-robot system, we can also think about kind of raising these properties into the team level guarantees, and I'm going to call those global guarantees. Okay, so you can think about safety of the whole team, making sure that no robot gets into a dangerous situation or into some kind of dangerous interaction with another robot. We can talk about throughput of the system in some kind of logistics domain. For example, we can try and maximize the whole throughput of the whole system. So a global performance objective. And in particular, we are quite interested in this type of guarantee. Our work hasn't been able to really achieve this kind of guarantee, but this is what we're aiming for. So guarantees that say things, for example, like regardless of the state of a team, with a high probability, if some user calls for my robot, there will be a robot there within 2 minutes. Doesn't really matter which robot will be there servicing the tasks for by the user. Just matters that some robot will go there. And how do we execute tasks across the team and still ensure that this kind of property holds throughout the execution of the system is something that we are very interested in. And a lot of the work that I'm going to show here is trying to build towards approaches that are able to deliver this kind of guarantee. Another very important final one consideration for multi-robot systems is the issue of scalability. So yeah, things scale typically exponentially with the number of robots. And yeah, you struggle to scale up these model-based approaches to large teams. We take that into account in a couple of different ways. First, we try to model these multi-robot systems compactly, and we try to use approximate approaches to solve the models, doing some heuristic search or trial-based search to solve the models. Furthermore, we also have this goal of exploiting the interplay between the local guarantees and the global guarantees. Okay, how can some kind of coordination system take the guarantees at each robot level and deliver guarantees at the team level? Okay, again, this is our main goal. A lot of the work I'm going to show here is building towards it, doesn't completely do it as of now. We are trying to really build two approaches that are able to do this. So given that, I structured the talk in a way that is going to look into what kind of guarantees can a given approach deliver. Before I go into that, let me just talk about kind of a standard model that's been known in the literature for quite some time to model multi-agent systems under uncertainty, and these are multi-agent MDPs. So a multi-agent MDP really takes the state space of each of the agents. So we have here an example for 2 and reasons on the joint state space. Okay, so for the multi-agent MDP, you are considering which position, the full state of Betty, the full state of Barney, and maybe some extra shared state features like states of doors in an office environment, for example, when you're doing your actions. Furthermore, your actions are also joint. So at each time step, each robot decides one action to take, and all of them are taken at the same time. Okay, this encompasses both the local models and the global model, because we have a model that basically takes everything into account, so we can get optimal solutions. However, there's a lot of drawbacks with doing things like this. So modeling it as multi-agent MDPs doesn't really solve the problem per se, but it's a nice thing to keep in mind for the rest of the talk. But yeah, so issues here. Scalability, we are looking into joint action and state spaces. So as I mentioned, exponential blow up as we add more agents. Can't really make the multi-agent MDP scale to realistic problems. There's also a lot of execution issues, and these come from the fact that actions for robots, the example we are looking here are mostly navigation actions. Actions for robots take time. Okay, so requiring a fully synchronized execution where at each time step, every robot needs to change state, communicate state across the team, figure out what to do, take an action jointly is very cumbersome and has a lot of requires a lot of strong assumptions over communication and over observability. We want to avoid doing this, so our models will try two different ways to avoid these problems. I'm going to give you an example of how this fully synchronized execution can be a bit clunky a bit further on. Okay, so as I mentioned, I'm going to structure the talk according to this global view, like team level guarantees, up down to a local view on the single robot guarantees. I'm going to start with a more purely global view, and this is multi-robot generalized stochastic Petri models. Okay, to explain what these are, I'll do it with an example. This example is quite helpful to understand what are the challenges that we try to solve using these GSPN models. And also, I think it's a nice example to show the kind of problems we are tackling within the group. So we have here an automated quarry, where we have these haulers that have some capacity to carry gravel around. And the goal here is to get the gravel that's being crushed by a primary crusher and the secondary crusher here and here, and take it to the unloading station. So our goal is to maximize the throughput of this system by getting to unload as much as possible. Okay, so this primary crusher is an automatic thing. It's just there crushing rock and creating gravel all the time. So you really need to ensure that there's always a hauler underneath the primary crusher at all times. Otherwise, it will start crushing gravel onto the floor. You get a big pile of gravel. Robots can't move anymore. You need to stop the system. Okay, so there's this big constraint over the system. We must have a hauler under the primary crusher at any given time. And then we have this performance objective of maximizing throughput of our multi-robot systems and unload as much gravel as possible. Okay, so what are the requirements for this type of problem? On the model side, I already discussed most of them. So we need models that allow us to model the navigation of teams of robots in some discretization of the environments and topological map. We want these models to allow for a synchronous execution of our policies. And we want this to scale to a reasonable number of robots. These quarries that typically had, I think, in the low tens of robots. In terms of specification, here we also have a slightly rich specification that considers the trade-off between two things. First, we have a safety constraint. So we want to ensure that there is always at least one robot at the primary crusher. So there's always one robot underneath the primary crusher, and there's no spillage. On the other hand, we want to maximize the amount of gravel that's unloaded from the haulers. So I forgot to mention the secondary crusher here is just an excavator that's operated by a human. And basically, haulers can go there and be filled by the human on demand. So the idea is if you have a queue of haulers here under the primary crusher and the queue is very long, maybe the new hauler should move towards the secondary crusher and get filled by the human, sacrificing a bit the safety of the system because there's going to be one less hauler queuing to be under the primary crusher, but still improving the throughput of the system because it's just not stopped here. It's going to get loaded somewhere else. Okay, so this is the kind of reasoning we want our system to do, taking into account the state of the team. Should I wait here to go under the primary crusher, or should I just bypass the primary crusher and get loaded by the human excavator? A point on this specification, both of these objectives are global. So they require us to know the full state of the team so we can solve them optimally, but they are independent of the individual robots. What does this mean? It doesn't really matter which hauler is underneath the primary crusher as long as there's one there. It doesn't really matter which hauler is unloading as long as we unload as much as possible. Okay, so there is a notion of independence from individual robots here in this specific problem that we try to exploit. And we exploited this by kind of abstracting away robot ID and thinking about robots anonymously. And to do that, we use generalized stochastic Petri net model. I'm not going to go into many technical details on how this works, but I have an example here of a fragment of the model modeling this part of the system here, so 2 nodes and an edge. And what we have is places on the Petri net that represent locations in the environment. So this place represents the secondary crusher, this place represents the edge, and this place represents this node here. We have immediate transitions that represent the triggering of actions. So this is sending robots between locations. And these ones we can control. Our policy will decide which actions we will be triggering. We have tokens that represent robots. Okay, so in this case, there is one robot that is present at this edge. So we have a token in the place that represents that edge. And we have exponential transitions that represent completion of actions. Okay, so these transitions are uncontrollable and they are durative. Okay, so they take some time to occur. The time they take to occur is stochastic and is according to an exponential transition that can be learned from data, for example. When these transitions fire, these tokens will move around the GSPN, updating the state of the system. Okay, so if you think about the full GSPN of this small model here, it would look something like this. We have 1, 2, 3, 4, 5, 6 robots in the system. And you'll notice that this is quite a compact model. Adding more robots doesn't require us to increase the size of the model. So that's one of the advantages we have here. Furthermore, because we want to give these probabilistic guarantees of performance, the rate of these exponential transitions is learned using realistic simulations. So the models are close to reality. Okay, so these GSPNs it is known that they can be translated into something that is called a Markov automaton. This is what you have on this side, and this represents the state space of the GSPN model. It's a generalization of an MDP that considers immediate transitions, but also exponential ones. And there are approaches to model check and to plan for this kind of model. Okay, so just to stress what are the advantages here, we have a synchronous execution that is naturally achieved by the GSPN model. So the immediate transitions that are triggered by the policy will correspond to sending navigation action commands to the robots. Then robots navigate and change state. When that happens, the corresponding exponential transition is triggered, fires the update states of the system, and then in the new state you might have a new action to execute, or you might need to wait for a new event to come from the system. And second big advantage here, they have better scalability than MMDP because they exploit the fact that we don't really care which robots do what, so robots are anonymous. However, this is still not perfect. It's still exponential, just not as exponential. But anyway, you can kind of scope your model. We have an example here of comparing the size of the multi-agent MDPs that you would have for different numbers of robots to the size of the state space of the Markov automaton that represents the GSPN, and you'll see that there's quite a sizable difference here. Okay, so then we can, given these models, we can start thinking about different specifications. We have this type of specification that I described before, which is untimed, and considers the specific constraint of always having one robot at the PC. And this can be defined just as some set of bad states that cannot be reached. We also have a performance objective that is maximizing throughput. This can be modeled as some reward that you get when robots unloads. And then we pose the objective as maximizing the accumulated reward until one of these bad markings is reached. So we try to get as much throughput as possible. When we get to one of the bad markings, the system stops and we cannot get more rewards. So the system needs to trade off getting as much reward as possible, but also making sure that these bad states aren't reached quickly. And we mentioned simulation to show that planning for this kind of problem allowed us to be much more robust to delays and to disturbances introduced to navigation. So by having these stochastic models of navigation using the exponential transitions, we were able to outperform handmade policy. Here you can see that this is the percentage of runs in which the safety constraint was not violated. the dashed lines are representing our approach in different configurations, and you can see that it's clearly above the handmade policy. So it allowed us to have some smart reasoning over these robot systems that we couldn't do it just by trying to do it by hand. The specification was quite conservative. So because robots stopped accumulating rewards when the safety constraint was broken, it was very easy. The policies were very focused on not breaking the safety constraint. So it was very rare for a robot to move to the secondary holder. And that we felt wasn't exactly what we wanted from the problem. So we started looking also into other types of specifications. In particular, we looked into long-run average objectives. And in this case, what we want to do is to maximize the expected throughput per time unit, or expected reward of the team per time unit. And we tested this in a slightly different model, or a slightly different problem. In this problem, we want to expect 3 locations here. And each of the locations has a different reward associated to it. So this will be more important. And we have robots that are moving back and forth, and they need to go here because there's a charging station. So this is for long-term auto style or long-term inspection use cases where the battery of the robots drains, and they need to go back to a charging station to charge once in a while. Okay, so we optimized for long-run average in this system, and it was quite nice that we can manage to show that by optimizing for the long-run average, which is the blue line here, we managed to get a more accumulated reward than if we had just optimized for discounted cumulative reward, which is the most standard way of posing infinite horizon goals for MDPs. So even though this problem is harder to solve, we showed empirically that from at least this problem, it is worth solving the harder problem to get a more effective or more efficient policy. This is also what I had to tell you about the GSPN side of things. They have strong limitations. First, the objective of the GSPN is only at the level of the team. Okay, so we can talk about objectives for different robots. And also it needs to be a style of objective where agents are interchangeable. So there's no notion of local state except the location of the robot. So the single robot model here is very, very impoverished. It's basically just a token in the multi-robot model. So we want, and we started exploring other ways of having richer single robot models. And that takes us to a view that manages to get a bit of this global view and global guarantees with single robot guarantees, so local guarantees. And this is an approach that we developed based on simultaneous task allocation and planning. Okay, just to give you a quick overview of what's the goal in this situation. We have a team of robots still navigating on a topological map, and we want to achieve a set under some safety constraints. And we also have assumptions on these tasks and in this model. So we assume that the robot actions are independent of the other robot states. So what one robot is doing doesn't affect with the outcome of the actions of the other robots. And we also have an assumption that the tasks are not conflicting and can be achieved by a single robot. So a robot doing something, the robot can achieve a task on its own. And by achieving that task, it's not making tasks for the robots unachievable. So there's these 2 assumptions here. And you have an example here where the tasks are just visiting some locations in the environment that are mapped in green, and the safety constraint is avoiding this dangerous area here that is depicted in red. Okay, so this is a quick overview of what these things look like. Now, how do we specify the mission? It's a bit richer than what I had in that slide, but just visiting. In fact, we use temporal logics to specify things. I won't get into details of on how temporal logics work. I just want to quickly say that we use the safe fragment of linear temporal logic to define the safety constraints. And these will be constraints at the team level that may ensure that no member of the team will ever go to a forbidden area or execute a sequence of actions that is considered dangerous. We model or specify the tasks for the system in co-safe temporal logics. which again allows us to do a bit more than just go visiting a location. So we might want to visit a location or a set of locations in a certain sequence, for example. And planning for that requires us planning at the robot level. On the other hand, we have the question of which robot does it, which task. So again, this is a question that is more on the team level. Just more specifically here, so we have a set of N robots. One has its own model, and you'll notice that these MDP models for each robot can be different. So the multi-robot team can be heterogeneous. We have a set of to achieve. We have one global safety specification that must be kept true by the team, and what we want to do is to find some kind of allocation that maps robots to a subset of tasks that need to be achieved. And these allocations should maximize this value here. So these allocations should maximize the product for each robot of the probability of the robot achieving the tasks that were allocated to that specific robot. Okay, so if you think a bit about it, you have the two parts of the problem here. You have a maximization here that is trying to maximize task allocation, and you have a maximization here at the level of each agent that is basically related to single agent planning. And what we want to do is to do these two things at the same time. So there are standard approaches to do this. One of them I already covered. You can just do the huge multi-agent MDP and use standard approaches for temporal logic model checking to build your policy. This would be optimal, but still super bad and has all the other problems already mentioned. You could also think about, okay, there's kind of this clear separation in the formulation between task allocation and planning. So I can do the same for to solve the problem. So I have single robots that plan for different tasks on their own and bid on the value of those tasks to some coordination entity that is running an auction, and this coordination entity then allocates different tasks to different robots in order to maximize the value according to these bids. Okay, so this is again a very standard way of doing multi-robot task allocation. There's a lot of works that do that. In fact, I'm also going to talk about some work that we have that uses auctioning, not exactly in this context, but still uses auctioning techniques. Problems here, it's suboptimal. Okay, so by detaching the task allocation from the planning, we stop being able to ensure that that the robots plan taking into account the full state of the team, and in certain cases that might lead to suboptimal behavior. What we did was was an alternative to these two approaches. So we considered a model that considers the full team, but doesn't consider the full team in a joint fashion. Instead of considering it in a joint fashion, it considers it in a sequential fashion, which is also quite common in multi-robot systems. And basically, you can see here, this is the model for robot 0, this is the model for robot 1. And the idea here is that robot 0 is going to plan and execute some tasks that are in the mission. And then at a certain specific states, it is able to pass the bucket to the next robot. Here we have an example of the robot passing the bucket, and then robot 1 will take the mission that's still left to be executed and plan for that mission. Okay, so we need to be smart on where these states to pass the bucket are. They need to be states for which you either have completed the task or have not started the task at all. And you also need to be smart in the way you sync the state of the system representing how much of the mission has been achieved between robots when you pass between these robots. You can do this, you build a sequential model that we call a team model, and you can do standard planning for this model. There is extra stuff that needs to be taken into account when robots fail to achieve tasks that were allocated to. And in that case, we need to do reallocation through replanning. I'm not going to get into details on that, but that's a big part of our solution to this problem too. So yeah, you have the paper reference in the bottom if you are interested in seeing that. Quick results, again, comparing to a full multi-agent MDP model. You see that our state space is much lower. We are able to solve the problem much quicker. And yeah, and in this case, I think even optimally. Also, yeah, so this is for 2 robots, and we are able to be able to scale to larger number of tests. However, there's limitation and some strong assumptions here. First of all, we don't model robot interactions, so each robots can cross each other, but in the model that doesn't really matter for the execution of the robot. There's strong assumptions on the interdependency between tasks. So what one robot is doing never affects what another robot is doing, and execution is in lockstep in this case. Okay, so we didn't, in this specific work, we don't have asynchronous execution. And if you look at the video, let me pull it a bit back, you can see how that yields a bit of clunky execution. Every robot needs to stop when they move, when they get into a new node before moving forwards, which can be, which can be a bit problematic. Okay, I think here we have a better example of that happening. So yeah. Okay, so that's led us to going further down in our way of looking into the guarantees that we give to these models, and look into a local view. And here we developed some work on congestion-aware planning. Okay, so as I mentioned before, in the previous model, robots would we would have robots going by each other, but in the model that wouldn't really affect the execution of the robots. But you see in this example, for example, that robots need to navigate along each other, and there's some delays as they go about. That one worked pretty well. We have another example here where robots need to coordinate to go through an area, and things take a lot more time. So yeah, these interactions are very related to the controllers that the robotics are using, and model well is very hard. So basically what we did was take these interactions between robots and model them as stochastic action durations, and this work has a very, very high focus on stochastic action durations. So in this work, we take local perspective, so a single robot perspective. Let's take a look at how that looks like for a single robot. Then also we have a goal. So okay, so each robot has a goal allocated to it. There's no task allocation here, and here's an example where the robot wants to reach this location and has a path. We have some distributions over the expected duration. They're quite peaky. There's not much uncertain. The robot is navigating without any other robot. Everything's more or less fine. Other thing, things start to get more interesting when we put another robot in. If we have Barney here that wants to reach this side, and these robots start executing at the same time, they'll have to get to a point here where they need to go around each other, and you'll get into all of those problems that you just seen in the videos before. So in fact, from Betty's perspective, if given that Barney is taking this path, the expected duration on this edge here is a bit wider, and the duration distribution is a bit wider, and the expected duration is a bit longer. So yeah, Betty needs to consider that when planning. So yeah, saying this in another example, you can see an example here for robots going down this aisle. This is data gathered from simulation, really. This is the the fitted distribution we get for 0 robots going down the aisle. For 1 robot, it shifts a bit to the right and gets a bit wider. For 2 robots, even more. So yeah, we need to start considering this. These distributions that we fitted here were learned using phase-step distributions, and basically what this means is that we have continuous time Markov chain models of duration, which means that we are modeling duration of the action of the navigation as sequences of exponential distributions. This is quite nice for 2 reasons. First, it allows us to, these phase-step distributions can approximate any continuous distribution. Second, they are good exponential distributions, which is very well with the Markovian assumptions that we know. And we exploited that. So we took the single agent model, we took the distributions of action duration given the number of robots in a given edge, and we created a big model that from a single robot perspective that is this time varying Markov automaton. So this abstracts away the presence of other robots into different congestion probabilities in different edges, and we can solve this problem by using sampling-based tree search. Okay, so now we have a way to plan for a robot given the paths of the other robots. Now, to plan for the whole team, we currently have just a sequential planning approach, where the first robot plans without considering any other robot, and then it takes its policy and inserts it into something that we call the probabilistic reservation table, and inserts a CTMC, that continuous time Markov chain that corresponds to its policy in the probabilistic reservation table. The second robot is going to plan using a model that considers the presence of the plan for the same robot in its congestion probability. Though we already consider what the first robot is doing, and so on and so forth, the last robot will consider every other robot when it's planning. So this is a sequential planning approach. Again, we compare this with two baselines. Baseline that just plans independently and might get robots into big levels of congestion. This is in green here. And one baseline that is based on multi-agent pathfinding, which is a standard approach to find paths for different robots, find non-conflicting paths for different robots. And yeah, so what we can see here, this is the main span of the problem, and we can see that the congestion-aware approach is able to find better policies than the other two by sometimes putting robots through the areas that have congestion if it's closer, but then if there's too much congestion, maybe sending robots around through an area where there's no robots. Okay, so that was kind of our work on this local view. I now want to change pace slightly and look into something that doesn't consider uncertainty, but considers a different problem multi-agent systems with is the question of cooperation. And here I'm going to talk quickly about multi-agent pathfinding as combinatorial Vickery-Clark-Rose auctioning. Okay, so what's the goal here? It's similar to the previous one. We have already goals for each of the robots. So Betty wants to go to this blue location, according to this yellow one. You want to find paths that are non-conflicting, meaning that don't. So this is more strict than our previous work. In this case, robots cannot go by each other. You can't have states where robots are close to each other, and you need to ensure that they stay sufficiently apart to avoid conflicts. Okay, and now what happens if we are kind of in some supermarket scenario and each of these robots is from a different provider? There's no guarantee that these robots want to cooperate to achieve their goals. So it might be each robot is only interested in achieving its own goal, and we need to devise approaches that incentivize these robots to first participate in our system and do what our system, the coordination system, tells them to, and second, be truthful about how valuable they think a certain plan for them is. And to do this, we basically framed this multi-agent pathfinding problem as a combinatorial Vickery-Clark-Rose algorithm auction. In this case, we're not auctioning off tasks; we're auctioning off paths in this environment. And the auctioneer is in charge of ensuring that the paths that are allocated to each of the robots are non-conflicting. Okay, so in fact, there's previous work that had done this connection between multi-agent pathfinding and combinatorial VCG auctioning. However, there were some or a lot of specificities of multi-agent pathfinding that weren't really taken into account. I won't get into details on that, but in fact, the approach scaled badly and didn't even consider that robots stay where they are when they finish their task instead of just disappearing from the system. So we provided an alternative approach that allows robots not to value all the possible paths beforehand. So they just bid on a smaller number of paths, and when there's no solution given the paths that were provided to the auctioneer, then we got into a descending auction phase where the auctioneer asks the robots if they are willing to accept a slight modification of the paths they submitted for a specific price. Okay, we were able to show that using this version of the approach with the descending auction when conflicts occur, so this is the red lines here. On the top, you have time taken to find solutions, and you can see that the red lines are clearly in this baseline from the previous work. And in the bottom, you see the average value that is obtained by the system. And again, you can see that our approach is able to not only faster, but attain better results. Okay, so that's what I had to say about that specific type of work, and I just want to wrap up, give you a summary of what I talked about here. So I try to separate our work into two specific views: a local view looking into single robot guarantees, and a global view looking more into multi-robot guarantees. And I have here a very coarse plot where I'll try to put each of the instances of the work. As you go here and here, you think about either local or global views being more fine-grained. So I started with these multi-robot, the GSPN systems that has quite a nicely fine-grained multi or team-level view of the system. The robot level view of the system is quite impoverished with being just one token. I also talked now later on this congestion-aware planning, which is in a bit in terms of our work on the other side of the spectrum. There's very rich models of duration given the presence of the other robots, and we can plan for those, but we don't do any kind of task allocation or think about team-level guarantees except the time taken for each robot to achieve its own task. There's also this work on simultaneous planning and uncertainty and multi-agent pathfinding as VCG auctioning. There is a bit in the middle. This has extra assumptions that these two works don't have. For example, it requires synchronized execution. The MAPF work currently doesn't consider uncertainty at all. We are currently working towards achieving that, but still this one does. What's our goal? Our goal is to push these works towards this area here. So this is where we want to get to. We have ideas on how to connect some of these works together to achieve better local and global guarantees in the interplay between, for example, plans obtained from a congestion-aware planning framework with some kind of auctioning approach would allow us to move more towards this area. There's a lot of things that we are currently thinking of that will allow us to move and push towards approaches that have a fine-grained view at the local level and at the global level and still are scalable. Okay, so that's our main goal. I hope the talk made it more or less clear. And yeah, that's pretty much what I had to tell you. I would just like to thank all the collaborators that participated in the work I presented here. There are just some photos on kind of chronological order of appearance in the talk. Thank you very much.
Nice. Thank you very much. Really nice talk. Also really interesting multi-robot work. So we'll now have some time for questions. I can see that Nick, you've already been busy answering questions in the chat, which is really handy. Good job. But are there any more questions from people in the audience? We've got some time. If you have questions, feel free to just unmute yourself and speak. So I think we have a question from Iran.
Hi. Hello, Nick.
Hello.
Hi.
Thank you so much. On that slide, so I'm not sure she's allowed to ask a question.
All right.
Well, I'm not going to ask a question from the part that, it was relevant to me. Thank you. Wonderful talk. Thanks so much. I have a quick question regarding the congestion-aware. Do you consider the direction within which a robot moved, or just the co-presence, for example, in a certain area is enough? So how do you compute congestion? Perhaps you said
in the model. Well, I did it. So in the models I showed in the experiments we have there, we abstracted that away, but we have ways of we are currently looking into ways of considering the context a bit better and seeing, okay, I'm in an edge, there's a robot coming in my direction, there's another robot that's coming from a certain edge that's still close to mine, so it might interfere with me. So we are currently looking into models that also take it into account. It's a simple extension. It's a problem of scalability mostly. Once you start considering these more fine-grained models of congestion, things scale worse. The model we have can more or less model that those more fine-grained interactions. But yeah, then being able to scale and plan for those for a big number of robots is more of a problem.
There are a couple of other issues as well. So one is, like, it's worth paying the price of the scalability because you get more accuracy. Sorry, close the door. My dog's getting excited. You get more accuracy in terms of the predictive power of the model, which we've been trying to do some been trying to do some work simulating robot behavior using the same model, and you see higher accuracy if you're more specific. The other problem, though, is that there's data requirements. So all of these transitions are learned from experience from robots in a team, and the more specific you make your model, the less data you have per sort of action in your MVP, and so it's harder to sort of populate the model from simulations or whatever. So we'd want that want to be specific, but it comes with some overhead.
Thank you. Thank you.
I've got one question as well. So I noticed there was an absence of, I guess, comparison to the various POMDP style methods. And as you probably know, there's a ton of work in this area. DEC POMDP is one of the kind of canonical models, but there's lots of other ones as well. For example, macro action, decentralized POMDPs as well. What do you, in your experience, how do your works relate to these, for example, the approximate solvers for some of these methods, and do you find they're applicable as well? One thing, for example, I did notice is you focus on the multi-agent MDP, which typically assumes that you have access to the state, right? There's no explicit modeling of of observation uncertainty. Does this mean that you have an external estimator and you just take something like a map estimate, which you take as the ground truth in your MDP style model? Or if you could give me your thoughts, I'd be interested.
Yeah, so first, the multi-agent MDP model is more kind of a straw person model. It's just it's kind of the more standard brute force naive model that one could use. We try to do different things. In fact, we don't do still partial observation. That's something that we haven't included in our models. That for now we are planning to. The main issue there is, again, we struggle a bit with scalability. So I would say that for the types of problems that we are looking at, we typically have enough of a communication infrastructure, and we can abstract away most of, at the level we are planning, we can abstract a lot of the state uncertainty and assume that we have a fully known model, and we can tell other robots what we are doing at least once in a while. We do try and avoid some of the communication issues with the asynchronous execution. But yeah, the works are very related. I decided not to really delve much into the DEC stuff due to time, but I would say there's a lot of things that we do that are in the same way. We have richer action duration models, for example, that doesn't happen in the DEC, of course, at the cost of considering fully observable models rather than partial. But yeah, so there's a bit of, yeah, you gain some fine grain in terms of duration, continuous action, size of teams. You lose the ability to do partial observability. Probably going to look into that sooner rather than later, I would say. Currently, we don't have anything.
Okay. In that regard, I think if you haven't seen those papers yet, I'd perhaps point you to this line of work on what they call macro action decentralized POMDPs, which is when they also deal with action duration, and it's kind of a straightforward extension that might be relevant to your work too. But anyway, thank you.
Yes, yeah. So it's I am aware of that work. The main difference there is that those action duration, they don't really reason about the time the actions take when they're planning. They allow for asynchronous action execution, but don't really have rich models of action duration over the same way we do. I would say, at least the ones I know.
I see.
But yeah, it's a very nice piece of work, though. Really.
Any more questions from the audience? I don't see anything in the chat. With that, thank you very much again, Nick and Bruno, for a really interesting and broad talk about the multi-agent systems activities in your lab. I want to say one more thing to the audience. This is if there are people in the audience who would like to speak as well, and please feel free to reach out to myself and Mike Woolridge. And if there is a slot available, it would be towards the end of the year, because we already have a bunch of slots filled up, but we still have some slots available. If you'd like to speak and present your lab, then please reach out and we'll try to slot you in.
And if you want to hear Stefano speak, you should also email him and tell him that he's not putting himself forward, but we'd like to hear him speak too. So
yeah, maybe a later time. So thank you again, Nick and Bruno, and thank you everyone for attending, and have a good week. See you.
Thanks for the invite. Thanks everyone.
Bye.
Bye.